it's probably the best kept secret in IT. We've got three real leaders to take us through confidential computing and to give us everything we need to know. So introductions, please.
Hi, I'm Mike Bursell. I am the Executive Director of the Confidential Computing Consortium, which is a Linux Foundation project.
I'm Mali Fontaine. I'm the founder and CEO of HushMesh, a cybersecurity startup in the Washington, D.C. area. And we leverage confidential computing extensively to reimagine the web itself. So the key pillars of infrastructure, the universal name system, and the universal certificate authority.
Good afternoon, I'm Mark from Anjuna Security. I head product. I'm also the co-chair of the Cloud Security Alliance Confidential Computing Working Group as well, based here in the US.
And Steve Wilson, I run a data protection consultancy in Australia. Identity. I started in identity 30 years ago with smart cards and hardware key media. A lot of us in this room, of course, have been obsessed with key security for a long time. So the idea of personal hardware, the importance of hardware-based cryptography, hardware roots of trust, is sort of second nature to us. But I'm going to get Mike to tell us why the time has come to see hardware-based cryptography and these techniques brought to the computing stack.
Okay, thank you. So firstly, I'll start by stating the problem, which is that it's about isolation. And typically, let's think particularly about isolation in the cloud. And when you do cloud, you're doing virtualization. And the way virtualization works is that it's great for two types of isolation and terribly bad for the third. So let me explain that. So you have a workload and you have a host. And virtualization is really very good at saying, I can stop one workload interfering with another workload, right? Type 1 isolation. It's also pretty good at stopping a workload from interfering with a host, which is type 2 isolation. So whether it's containers or VMs or hypervisors, we're pretty good at stopping that. However, the whole way that virtualization works is that it's terribly bad at type 3 isolation, which is isolating the workload from the host. So that means that if you have control of the host, or you have kernel access or hypervisor access or admin access to the host, you can look at, change, do whatever you want with any workloads, because that is literally how virtualization works. And this is suboptimal if you've got sensitive data or sensitive workloads that you're trying to be dealing with. And it's not just in the cloud. This could be in-house. It could be on a pole for a sort of an edge use case, or in a stadium, or in a hotel, or in a casino, whatever. But typically, it's in the cloud that people start caring about this. And the problem is that you can't really fix this without doing something at the hardware level. And 10 or so years ago, the hardware vendors started to realize this. By the hardware vendors, I mean the silicon vendors. And so now we have capabilities from Intel, from NVIDIA, from AMD, from ARM, from RISC, which provide chip-level capabilities which allow you to isolate workloads from the host. The basic way they do it is by encrypting or otherwise stopping anything other than the CPU looking at memory pages. That's what it does. And that's all very well. There's one more step, which is that you need to be certain that it's been set up right. And so each of the technologies has something called remote attestation, which allows you to not only provide a cryptographic measurement of what's in these memory pages, this workload, but also then to verify it on a third party. And it's very important that the third party doing the verifying is not the person who's hosting it, because if they are, then what's the point of doing it in the first place? Because you're just trusting them. So that's a very lightning overview of what confidential computing is. It's chip-level, hardware-based isolation and protection of integrity and confidentiality and attestation on top.
So it is as if our cloud computing workload is sitting in a machine with a common architecture with hardware-based cryptography all the way down through the layers. It's as if we've got better control over this amorphous cloud computing object.
Absolutely, and it means you don't need to trust the OS. You don't need to trust the hypervisor. You don't need to trust the cloud service provider. You need to trust the stuff that's in what is called a TE, trusted execution environment, which is one of these isolated bits, and you need to trust the chip. And in all cases, you can trust them because you have cryptographic checks that you do on every single time you do it, which means that you have that assurance through
So
cryptography.
my sort of editorial contribution at this point is to say to people there's two takeaways today, I think. One of them is the T's, the trusted execution environments. We're going to talk about that. And attestation is the thing that I think really makes the big difference between, well, we've always, some of the cloud providers have had hardware security modules, HSMs in the cloud for a while, but no attestation.
Yeah.
So
That's
we're
my
also
work is
gonna-
done. I can leave now, right?
We're also, you need to tell us more about the consortium as we go. I want to know about the big brand names that are in the consortium because it's really important. We're going to keep things reasonably nimble today. We do want to take questions from the audience. We're a bit hampered. There's only, I don't think there's any runner or microphone. So if you've got a question, just shout out, wave your hand. We'll hear you and we can replay the question. So think about that for a while. We've got a few more things to go through. We'll take questions in 20 minutes if you've got them. So I've already hinted that I've been playing with smart cards for a long time. I know that Mark has. We've had access to hardware-based computing for a long time, hardware-based cryptography. But what's changed, guys, in the last year or two to actually bring the confidential computing consortium to the fore and to make this thing real? And we might go to Mark. What's changed?
Sure. Thanks, Steve. So if you look back over the last decade of confidential computing, it all started with the notion of creating isolated compute, where you can measure trust, figure out that you've got an environment that then you can put sensitive data and code in. And back in the day, these are quite complex environments, also somewhat limited. But the modern equivalents of this, which are now widely available across the clouds today, I mean, you can go to most of the, or in fact not all of the hyperscalers and many managed service providers and have instances that have this capability in them. And it gives you the power to do things at scale that's unprecedented. And so my view of the world, from my personal perspective, looking at it through the lens of the customers that I work with, is that the future of compute will be confidential by default. It is not today. But the roadmaps of all of the chip vendors and all of the providers have this backed by billions of dollars of investment. And that's to protect themselves from risk. And it's to offer capabilities to protect you from yourselves and you from attackers, which is always a really difficult problem to solve. Mike, you're waving your hand here and want to say something.
I missed something, which is important. I talked about chips, and you may have just assumed CPUs. It's absolutely GPUs as well. And that's really important because that's the other thing that you may have noticed over the last sort of 10, 12 months, maybe, this AI thing a little bit. So we now have capabilities to allow AI workloads to be using confidential computing as well.
GPU is a GPT processing unit these days. Less about the graphics and
I'm really old school, so
Nana, what do you think has changed to make this important now?
So I think there's one more piece to the confidential computing landscape that's very interesting is that, so not only do we verify the workload, but the chip itself, is cryptographically verifiable, so it is endorsed by the chip manufacturer. So what the chip tells you, you can trust because the hardware itself is verified. And then there's another super interesting property that was not realized before, is that at least in the technology that we use, and I believe it's true for all confidential computing environments, trusted execution environments, you have true or high entropy, high quality random number generation within the trusted execution environment. The reason this is truly transformational is that until now, keys had to be managed and generated separately in a remote environment, in a HSM or some distinct computing environment that is specialized for key management. And then you had to rely on human trust to just say, this key belongs to this process, and that key or that process needs to go and get the keys from that HSM. And the quality of the HSM, the quality of the backup of the HSMs, the key management aspect of things were completely outside the verifiability of the system, right? You can't verify those things. And so this brings us to zero trust. I think what's really amazing about confidential computing is that it enables you to have a zero trust model that goes all the way down to, the chip itself. You verify the chip. Zero trust, by zero trust, I mean never trust, always verify. So verification is a word that we use a lot. You verify the chip, you verify the code that runs in the trusted execution environment. It's not just the code, it's the entire configuration of the TEE itself, so memory paging and all that. And then you can verify the cryptography because you know that keys that are generated within the environment are coming from the environment and is of high quality, and then you can verify your cryptographic primitives, and then from there you can do all kinds of magic. You can do key management and data, security in a way that could not have been done before. So before I give you the mic, we forgot to do a quick show of hands. Who in the audience actually had heard of confidential computing before? That's a pretty good number. It's about a 50%, right? 40-50% split. And who is actively using confidential computing today? That's many fewer. So
Did you do that poll at RSA?
I did not do that poll at RSA. No, I didn't have an opportunity to do
Certainly
that.
in more generic computing meetings in the last 4 months, and the show of hands is less than 10%. It's incredible.
Yeah, I'm saddened but not surprised.
Mm.
One thing that's probably worth noting is the difference between TPMs and TEs. Sometimes you get confused, and they offer some similarities in that they're both in hardware. They could both be used for crypto, and they've both got hopefully decent entropy. TPMs are very limited in what they can do. They also have a memory that can exist over boot times, which TEs don't. But TEs allow you to do generalized computing. So you don't have to be, you can do whatever you want. You can write your own application. It could be anything, depending on.
So emphasis on execution environment.
Yes, exactly. Yeah.
So
And you
it's a
can-
whole computing capability.
Yeah.
Unfortunately, it's got the T word taken on the front, because we've already heard that we want zero trust, so anyway, that's a different hobby horse of mine. I get the impression that the TPM versus TEE is almost like a standards thing, like this separate worlds. The CCC, the Confidential Computing Consortium, is going to become the standards body for TEEs?
I'm unclear. We haven't decided. We're in fact kicking off a work group. If you're interested, come and join us. So the TCG is very specific about what a TPM looks like.
TCG, Trusted Computing
Trusted
Group.
Computing Group, yes, they've been around for a long time.
15 years looking after
Oh, if not
TPM.
longer, yeah, absolutely. The Confidential Computing Consortium is the industry body. It's part of the Linux Foundation. It's got all of the major chip vendors, ARM, AMD, Intel, NVIDIA. We've got people like Huawei and Oracle and TikTok. TikTok really interesting because they have a huge they really need to be able to prove to folks that they can't mess with data and they can't look at things, and they can use trusted execution environments to prove that they can't mess with stuff, right? So actually, there's a good reason for them being there. But lots of startups such as Hashmesh, I don't know if Angina counts as startup still, but they've been around for a while. Microsoft there, Google, Meta, all those sorts of folks as well. Although we're not officially announcing it yet, we're just doing a zero-cost startup membership where you only have to pay your Linux Foundation fee. So if you are a startup and you're interested, you can get 12 months for free. So we'll be announcing that next week. It's not official, so shh.
So that's a good segue, thanks Mike, to Mark, and God, you gotta have a 4-letter name starting with N, don't you, to be honest?
Yeah.
No, I don't know where that is now.
It's not the only 4-letter name, I mean.
So, now we know about the dim view that Identiverse has towards pitching, and we've all gone through the editorial process, but nevertheless, Mark and Manu have got skin in the game because they know what they're talking about. The people who know what they're talking about are doing things. So with some caution, I'm going to ask you two guys to tell us what you're doing and why confidential computing is powering what you do.
Yeah, so in a nutshell, what we do as a business is create software to enable very seamless and simple use of confidential computing. And that's taking away the friction and complexity of deployments. How people are actually using this, though, is probably what matters. If you were at the RSA show last week, you might have seen some of the public announcements we made. We're doing projects with people like the US Navy, with NVIDIA for confidential AI on the confidential GPUs. Very powerful and interesting projects. One of our clients is a large bank, and the problem that they were trying to solve was they didn't come to the table and say, we need confidential computing. You know, it's like a lot of cryptography. People don't wake up, well, I do, but other people don't wake up and say, I need advanced cryptography for something. What they want to do is solve business problems. And in their case, they had this opportunity that's represented by their data, essentially. And they work with lots and lots of retail partners with lots and lots of identity information. And ideally, there was the need to be able to combine these data sets, to run models on them to explore the data for new things, like optimizing market, optimizing top of funnel analysis, all sorts of interesting things that you can do with data. And the traditional ways of doing that are things like synthetic data, anonymization, and so on. But if you're using more advanced machine learning and AI, you need the full fidelity data to create the model that's going to give you the best outcomes. So how do you manage privacy and complexity in those scenarios? And so confidential computing does let you create essentially what is I call a clean room environment, where you can merge data and models that only that environment can operate on. And then you can get the results out with full privacy guarantees. And so this isn't thwarting regulations or anything like that. This is actually complying with regulations, but allowing you to do things by essentially fully anonymizing the compute itself, and then having evidence and trust. Coming back to the trust, the mechanisms, and being able to do that in a cloud where you may have natural paranoia, like a lot of organizations, about trust and security and so on. And so it's giving control back. And so we're seeing this pattern emerge over and over, where organizations can collaborate very effectively because they can create a secure environment that can be used for scaled compute. And when we're talking AI and LLMs and things like that, you are dealing with some pretty massive data sets. So I think we see that one, and obviously there's the other one, which is unblocking things like cloud migration, where there's always been hesitation because of privacy and security. Despite all of the best efforts that the clouds themselves put in place, they can't always take themselves out of the picture. And confidential computing absolutely lets them do that. So I think these are the kinds of things that I definitely see emerging, particularly in financial services, highly regulated industries, retail. And a lot of that data is identity processing, which is obviously under various privacy regulations.
I'm going to ask you to say more about identity in a couple of minutes. Manu, what are you doing with CC?
Yeah, so as I said very quickly in the introduction, this is an important fact. We are a public benefit startup. So we realized very early on that what I'm going to tell you has a public-private partnership type nature. So when we realized that confidential computing was becoming usable, which was just a few years ago, we set out to revisit the underpinnings of the web itself. We figured out the blueprint of what we call the mesh, and the mesh is a internet-scale global information space, just like the web, but with automated cryptographic security and universal zero trust across the entire information space. And I know it sounds outrageous, and like nobody's going to reinvent the web and all that, but if you put things in context, and you think about the web being a 35-year-old technology that was designed for scientists and smart people to share data, and everybody was trusted in the environment, on the network, there was zero security built in. And the architecture of the web itself requires privileged insiders everywhere, from the DNS all the way down to the DB admin. And when we realized that confidential computing solved that fundamental problem, the physical identity of the hardware, the chip itself, that we could verify that, and then that we could build the different layers and verify every layer, and that at the very top we could then automate decentralized cryptography. That's when we realized that we could create a global infrastructure that would enable the signing, encryption, decryption, verification of every single bit within the information space. So anyway, long story short, we are developing two key pieces of infrastructure: the universal name system that generates random identifiers for every entities, people, organizations, physical things, digital things, and the universal certificate authority that automates decentralized cryptography, including key exchanges between individual entities.
So I know that Mike's got something to say, but to editorialise, you're talking about some themes that overlap with identity, but they're much bigger than identity, but things like the attestation of the hardware, true random number generation, and definite hardware, certainty of the hardware.
And that's kind of where I was going to go, in fact, and thank you for setting that up, which is that what I think is exciting about this stuff is it allows you to think in new ways. You have new primitives, and that sort of go back to the title of the panel, the internet's missing cryptography engine. There's things you could do that you couldn't do before. And if you think, okay, if I can be sure that what I think is running, because I've got cryptographic assurance of it, if I can be sure that it has access to decent entropy, because I know that the environment's been set up in is one that I understand, and if I don't care where it's running, what can I do differently? What does that mean to my business? What does it mean to my organization? What does it mean to the governments that I work with the charities, with the individuals I work with? How can I think about the world in a different way if I have these new primitives? And Manny's given an example, and we've had one had some from Mark as well. And I did a birds of a feather thing at RSA a couple of weeks ago, and people came from Dell, people came from a Capital One startup, but we had someone from a pest control business. And I thought, yeah, of course there's stuff that they want to keep. Yeah, thank you, yeah. But there's stuff that, there's privacy data, there's stuff that they have to be protecting. And if they can use it, then, surely everyone should be thinking about the US Navy for pest control. I suppose you could say they do the same job, but, hey. It's about new primitives and what can you be doing. And identity is absolutely a whole set of opportunities to be using these technologies.
In privacy, there's a bit of an obsession with jurisdiction. So here's a question on notice, if you like. You said you can compute without caring where your compute is happening. Of course, in privacy, people are caring more and more. And one of the great dilemmas or wicked problems at the moment is how do you have a cloud that's jurisdictionally specific? I'm assuming that you can configure a confidential computing workload so that you do, in fact, know where it is if you need to.
That's a very interesting question,
and you can take that on notice if you like.
I'm going to say you shouldn't.
Maybe you need to sometimes.
I don't think you do need to, even ever. But that's a conversation we can have, because what you're doing with a trust execution environment. Sorry, I've written a book about this. I care about it. Is basically you're extending your trust domain and taking something which is in another trust domain and moving it into yours. So it shouldn't matter where it's running, because it's the chip that you're verifying, not where it runs. I shouldn't care if it's in China, or if it's in Iran, or if it's in Las Vegas, because I can be proved that I have control over it and no one can mess with it.
Okay, control, Mark. I think what you're saying though, and I tend to agree with you, but you're talking about the difference between what should be and what ought to be.
That's right.
And what
There's a difference between should and
change.
can.
Yep.
Very big difference between should and can. Should Steve be wearing 2 different socks, for example? I think he should. And
He does.
So, Mike is right. The confidential computing does give you that ability to compute anywhere without control, but it also does give you, in some circumstances, provenance of where that happens, which is important from a regulatory standpoint. When you think of an operation that must take place within a particular favourable regulatory regime versus taking place in another, that can invoke a liability problem for a business.
Yes.
In wealth management, this is a big deal, for instance. In blockchain processing, it's a big deal where transactions take place, because you may want them to be in a regulated environment to avoid falling foul of the law. So these actually are powerful constructs that confidential computing can also give you, in addition to the anonymization, if you so wanted.
Yeah, we don't know how that's going to play out in the next 5 to 10 years. The tensions between the privacy paradigm, the privacy point of view versus the reality of the cloud is at odds. Manu?
Yeah, and I just wanted to add to this. I think we really have, the best of both worlds. We can, completely ignore where it runs, but we can also pin exactly where it runs. But I think, just to bring it back to the identity audience here, I think of all the workloads that should run in confidential computing environments, identity, authentication, authorization, key management, and all of those things should be the first ones to actually run in attested, trusted execution environments because of privacy, anonymity requirements, non-repudiation, if some of you are worried about that, provenance, integrity, of all the data bits, the identifying bits about people. So this is why we actually wanted to be here, because this is a fantastic place to start.
Well,
It's with the identity.
That's a great segue to identity. I'm just going to remind the audience that we've got space for questions if anybody's sitting on something.
Before we do that, Steve, there's one other thing I want to add to the picture.
We haven't talked about this yet, but when you think of data security and what we've had to do to get to what we think of as secure over the last few decades, it's usually involved very high amounts of effort on developers to integrate toolkits, to manage keys, all of that sort of stuff, right? So, I've been in this industry for so long, known Steve forever, just the burden on developers, which is essentially, it's not adding business value, just encrypt, decrypt, those sorts of things, anonymize, de-anonymize. That's really expensive. And I think one of the things we haven't talked about here is that confidential computing is something that is instrumented into a development process. It's not something that you have to build in. And so truly it is adding that shift left capability so you can turn on security as opposed to have to design it in. And that is a very, very big difference between the classical approaches where you would have to think in advance and invest in advance. Now you can make decisions based on the risk profile and the cost. Put the workload where you want it, and then have it run essentially isolated with hardware proofs. That's a big deal. And it is a shift, and I think that's...
And with the chain of provenance and certainty going down.
With the proofs and the certainty, and
you said effort before, and my mind went to key signing ceremonies, which are
I was
not
in the
just
payments world.
themselves
You do this forever.
labour intensive, but designing a key signing ceremony can take months.
That's right. Sacrifice the chickens, get those smart cards out of the safe, sacrifice more chickens.
Hold hands, turn
Really
around.
sorry for them, but we need to get those pin keys.
And meanwhile, everybody's freezing to death in the data centre.
Yeah, and film, yeah.
So we are going to go to identity, and we'll get Mark and Manu to concentrate on these two questions. But Mark, can you tell us more about key management? How do you think about key management through the confidential computing lens?
Key management, a favourite topic.
Yeah, I knew. And you've got 2 minutes.
So I mean, key management, again, coming back to what we said earlier, it's often been something that had to be done in the realm of HSMs. And I'm not saying HSMs are bad. I used to run a HSM business, I know what it's like. It's important, and there are certain classes of HSMs that must be used. But when you think about many processes, they often rely on either a token to get to a HSM, or taking a HSM out, a key out of the HSM, or decrypting something locally. And all of a sudden, now you've got the keys, you've got the cryptographic process, you've got personal data, you've got everything else that's essentially exposed.
Manual labour.
Manual labour, very high risk of compromise. And it can be as simple as a memory dump to somewhere that then gets moved from production to test, and now you've got something that can be even more attackable. That has happened. So confidential computing lets you wrap all of these processes in the hardware isolated ecosystem. And it is not just about simulating what a HSM does, that would be very inefficient. You can essentially wrap and shroud your whole application and run the whole thing in these types of environments. And so now you're really sealing off the insider threat, the risk of a zero-day compromise getting access to something, and observability by people who shouldn't. You can still run your monitoring, you still run everything else, but you shouldn't be essentially exposing those keys in memory environments or to people. And so this leads to this notion of identity, and what Manu was working on, mentioning before. So when you think of identity, the big difference with confidential computing is today we give identity to something, and we hope that that something can hold on to that, like a key or a hash or something like that. Whereas confidential computing can create the identity based on itself. And so you're creating inherent trust that you're not having to give out first. And so this lets you then start to prove that you're running a trusted infrastructure and then use that for the identities to pull in secrets and keys and other things.
When Mano and I first met, he was fond of the phrase inherent authenticity, which has got lots of syllables, and it took me a long time to twig that confidential computing allows, you know, the very existence of data to almost, I don't want to say self-verify, but the existence of data in that environment is inherently real. There's only one way for it to get there.
Yeah, and to complete the story, when I told Steve about inherent authenticity, he said this is word salad, much less syllables and very explicit. So it took me about 3 months to just turn it around and because I couldn't express it very well at the time, to be clear. But just to talk about
tell
that
us more about tell us more about that and
yeah,
the relevance to verifiable credentials, for example.
Okay, so just to continue what Mark was saying, you generate identity from within. So think about, you have a computing environment, a trusted execution environment, and you generate a random number within that environment, and you make it big enough. Make it 256 bits, right? Because that's, if you do the math, you know, that there's enough of those unique identifiers for every particle in the universe, roughly, right? Who's counting, right? And at that moment in time, that number only exists, both physically in space and in time, only exists in that physical chip, in the entire universe, across the lifetime of the universe. Because the likelihood of this same number to happen a second time in the history of the universe in a separate chip, you know, with a good source of entropy, of course, that's the key, right? Is that the entropy needs to be very, very high, is close to 0. So you actually have, when you use a TE and you generate a random number that is large enough, you have a value that cannot be observed by humans, which means it cannot be copied, and it cannot be guessed because it's truly random, and it cannot be brute forced because it would take, you know, multiple lifetime of the universe. So you have this concept of inherent authenticity, and then you can do cryptography with it. That's the executional, the ability to run general purpose code on this thing. So you can do key derivations, which enables you to do wallets, which brings us to verifiable credentials. We just, you know, we are in the cohort, the latest cohort of the DHS's VIP program to do privacy preserving digital wallets. And what's interesting is that the concept of an identity wallet is underpinned by a keychain. Well, guess what? Those keys should be generated in a confidential computing environment because that's the safest way to do it. You protect it at generation, at birth, right? And then you can start doing operations, you know, on those keys to create a keychain, as we call it. So in our view, every entity, right, as I was saying in the beginning, should have its own unique cryptographic identifier, and then ends up having its own keychain, and then ends up having its own wallet, all in an environment that is itself verified and is completely isolated hardware. So protected from the host, protected from everything else. So to bring it back to zero trust, you end up with what we believe is the smallest attack surface technically possible. And we're not talking about 20 or 30% better, we're talking about many orders of magnitude better, because you verified absolutely everything along the way. There are still some, you know, trust base, you need to trust the chip, you need to trust the code, you need to, but at least you're grounded in not certainty, but in verifiability all the way down. So,
you were skating around key links before to the 256. I just it doesn't matter how geeky you are. It doesn't matter whether you've got a PhD in pure maths. In fact, if you do have a PhD in pure maths, I think you're liable to just take some of the stuff for granted. I know I do, without a PhD. But we talk about millions and trillions and squillions, and it's really worthwhile finding a website. I think it's called How Big is 2 to the 256? If you search that, you'll find it. And read that and think about it, and think about what Manu's been saying about the uniqueness of a key. These are not just big numbers, they are profoundly unique numbers, and it's worth just taking some time to read that website, I reckon. Mark's got something else.
I was going to tell a story about
Person,
this that's related, and it comes back to how confidential computing can enable completely new ways of doing things, like you were describing. So, one of our customers, it's a payment company, and they're actually serving underserved markets in places like Argentina and Turkey and so on. And what they were doing is creating a wallet that allowed their customers their families to send money to their relatives in country and back them against, say, US dollar or EU, because the local currencies were going up and down so much, losing value even immediately after the transaction. At the end of the day, they needed to create a wallet. And so they started out by creating the wallet on the phone itself, because that's something you possess, but that's not a secure environment typically. And that will take about a minute because it's not computationally very powerful. So generating big prime numbers and things like that. But that's not a good experience. You know what 50 seconds looks like on a phone to somebody sitting waiting for something? It may as well be 50 years, right? So by shifting that process to the cloud, they could speed things up, but you can't pre-generate numbers and have trust in them if you have them sitting in open compute. And so if you use confidential compute, essentially what they're able to do is pre-generate all of these numbers. So when a customer needed a new wallet, they were able to do it in about 0.5 milliseconds. And so you've gone from a minute to 0.5 milliseconds, and you're doing it in an environment where you don't have to have all this extra software for creating what is a software zero trust environment, which is never really truly trusted. And so it gives, the reason I bring this up is it lets people think differently about how they can organize their applications to do things that maybe even orders of magnitude faster, because you can do things in a trusted environment. And so by just doing that, suddenly they were able to launch completely new products because they were able to do things fast, turn wallets on and off dynamically. And so I bring this up because it comes back to the trust, keys, and other things that it's going to be very important for everyone to kind of understand, because I'm sure it's in people's future.
Manu, and then Mike.
Yeah, I really love the fact that you brought up the speed thing. There's another property that's very interesting once you operate in trusted execution environments, an environment that can keep secrets, is that you can go from, in many cases, you can go from asymmetric cryptography to symmetric cryptography. You can manage secrets in a way that you have assurance that they're not going to get leaked. And that gives you, at least an order of magnitude better performance, scalability, and it gives you quantum resistance. That's another thing. We need to talk about 2030, 2035, when it's going to be mandated that all cryptography be post-quantum or quantum-resistant cryptography. So there's a whole slew of things on the horizon that are just saying, you know what, you should run in confidential computing environments. And it's kind of a shame that it's not better known. One more thing that I want to say, and I'll give you the microphone. The verifiable credential world has been around for about a decade or so with SSI and that movement. What's interesting in the words verifiable credential is the word verifiable. It essentially admits and asserts that the web itself is not verifiable, that you need to do all that other stuff, right, to suddenly have just a few bits, just a few claims in a signed statement, right, to make that verifiable. And yet, you cannot verify the cryptography. You have no operational security signals about the keys, who signed it, the binding of the keys, and all that good stuff. All of those things change when you start from a place of trust, or a place of verified trust, I would say, a trusted execution environment that you verify, because now you can bootstrap everything in a way that was verified to begin with.
Thank you. There's one thing that I care about a lot, and I'm just going to have a bit of a rant about it. We've used the word trust quite a lot in the last few minutes, and I want you to distrust that word a lot, because I don't think that what I think it means is the same thing as what any of the rest of the other people, and any of you, I think we all disagree about what the word trust means. If I say I trust my sister and my brother with my life, my sister's a dive instructor, my brother's a doctor. Does that mean something different to I trust my bank? Does it mean something to I trust my banking systems, my banking system's APIs, my banking system's applications? And we need to understand what trust is, and I wrote a book because I care about it. I'm not going to ever make any money out of this book. But trust and computer systems in the cloud, please have a think about what we mean by trust, because until we can all agree on a framework for what that is, and I'm not saying that I got it right, but at least there's something to discuss and disagree with, we're in a difficult position. And it's really important for identity as well, because if we don't know what we mean when we trust an identity, we're in a really difficult position. So just a bit of a rant, sorry.
And you find yourself leading an organisation that's all about standardising trusted execution environments.
We are not about standardization. Yet.
Adoption. Good segue.
And open source as well.
We want to wrap this up by talking practicalities. So hang on to the mic. Mike, talk to us about pathways to adoption of confidential computing. I think that this is the future of the cloud, but how do we get there?
Sure, so I'm a big open source guy. I've been using Linux, my main operating system, since '98 or so, so it's really been a long time. So one of the things about the Confidential Computing Consortium is that it's part of the Linux Foundation, and we promote open source projects. So we have, I think, somewhere between 11 and 14, it's just been going up, different open source projects which are part of the Confidential Computing Consortium, and there are more joining, and we encourage people to be using that. Apart from that, there are a growing number of ISVs and other implementers, not to mention all of the hardware providers and the CSPs, the hyperscalers, who are members of the Confidential Computing Consortium. And it's a great place to have these discussions, the technical discussions, the business discussions, in a sort of safe, non-antitrust competition type place. And I hope that both of these guys benefit from that. So if you're interested, please go to confidentialcomputing.io, come along. You don't actually need to be a member to come along to the meetings. Yeah, I'd love you to become a member, but we just want engagement. So please, that's a great way to start. Mark, I expect you have some things to say as well.
Sure. A couple of things too. I'd also, if you're really interested, you can also look at what we're doing in the Cloud Security Alliance, which is related to the CCC. So it's looking at the governance patterns for confidential computing, the cloud controls matrix, and there's a lot of work being done over the last 12 months there, which is great. I think I'd also just wrap by saying that, I've mentioned some, large banks and the Navy. It doesn't have to be organizations like that. We have startups like that payment company. You can be really, really small and start well with confidential computing as a way to avoid having to go through some of the machinations that you typically would do with software out of the gate. And so having this ability to protect at a completely new level is very distinctive. And you think about the software arms race that we've been in over the last couple of decades, we're always trying to stay ahead of risk, trying to stay ahead of attackers, and it never stops, except when you get down to hardware that is essentially immutable and itself also evolving. That's a very different end game for security. And I think for the first time, the conversations I have with organizations are, you know what, this is something that actually can make me sleep better at night because I can actually prove it instead of just conjecture on something that might be undermined tomorrow. That's a big difference. So something to think about.
Yeah, and to connect it with what Mark just said, I think every organization is talking about zero trust today. And I think confidential computing must enter that conversation. Because I participate at the IETF, and we see a lot of discussions about protocols and all kinds of things. But the idea of bringing everything down to the physical chips is, we believe, absolutely necessary. And the reason I'm saying this is because, yes, it's great to have a great zero trust initiative and to trust that you are doing the right thing in your own domain, that your IT guys are the best and all that. The problem is that nobody lives in isolation. Right? Everybody is connecting to somebody else, and now you have to trust the other guy. You have a third-party risk. So there's a dimension here in confidential computing, which is not just verifying for yourself, but verifying and providing evidence to others that what you do is right. So, and that's the reason, a tiny plug, that we exist as a public-private initiative, is that we do believe that eventually the whole idea is to interconnect people and organizations and workloads and things in a way that has global verification, not just local verification. So you should start now, you should bring that into the zero trust discussions, and then you have to admit and recognize that it's not good enough to say you have zero trust, but you have to trust my people. You have to trust my insiders, and you, outside my domain, have to be blind to what we're doing. You need to be transparent about all that, and we need to remove, the human elements from the information space itself, so that we don't have to rely on human trust. We can rely on zero trust, on verifiability of the infrastructure.
Final word on standards, participation, accessibility of this technology. What's ahead, Mark?
I think Mark was right. It's going to become everywhere. If you talk to Microsoft, they expect that 90% of the workloads on Azure will be running confidential computing in, 5 years, 6 years. I can't remember the numbers, but they're absolutely seeing that, and we're seeing other people saying the same thing. It's going that way. Now is the time to get your foot in the door and understand it, because it just changes how you think about stuff.
And so what that looks like in terms of a pathway is that the processes themselves are featuring TEs, and the cloud providers have an attestation service that's bolted in.
So one thing that's missing is a good attestation service model, because you shouldn't trust the cloud service providers to be attesting their own stuff. It's like marking your own homework. If I say to you, please set this stuff up because I don't trust you, and you say, oh yeah, here it is, and I promise that it's okay. No. So one of the things we're working on in the confidential computing source is, what does that look like? Who should be running these things? Should it be public-private partnerships? Should it be regulators? Should it be ISVs? Should it be the customers themselves? We don't have answers for that, and that's a conversation that we're actively fostering.
Fantastic. Lightning round, people. What message do you want the folks to take away today?
Give it a go. That's what I would recommend. It isn't something that is that hard to use, at least, compared to how it was many years ago. And it's also something that can be widely applicable. It doesn't have to be to cryptographic systems, and you don't need, experts to use this. Have a go. Start with a simple project.
That's an interesting point. Everything should be secure to the same level. Let's stop titrating security.
Rewinding the tape a little bit here, but you probably have confidential computing in your pocket actually today to a limited extent. So when you think about biometrics, good thing to take away. In the iPhone, there's a little chip that handles the biometric verification process, and you probably recall Apple denying requests for access to iPhones in certain conditions. It's not because they didn't want to, it's because they couldn't. Because that identity was only known to that chip. That is a very small confidential computing environment. It's in a trust zone system. But it binds your biological data to the camera, to the chip, and it says yes or no, it's you. That's it. And funnily enough, when you have to go and trade in your phone, if you don't turn off the, the Find My Phone feature, that's the biometric that unlocks it. And Apple can't break that. So you can never get your refund. So it's in your pocket.
Manu, wrap up. What message?
Yeah, so give it a go. There is a little bit of a learning curve still, because you have to think indeed about going all the way down to the hardware, so the skill set is a little bit tricky. But there's a reward. It's going to pay off, many orders of magnitude more, because on the back end, there's a whole lot of problems that you don't have to worry about any longer. So it does pay off to invest upfront to the security right all the way down to the chip, and then there's a gazillion things that you don't have to worry about.
Cool. confidentialcomputing.io, Confidential Computing Consortium, or find me on LinkedIn.
All right, thanks very much, Mike Bursell, Manu Fontaine, Mark Bauer. Thanks for sharing today, and that's a wrap, folks. Thanks.